we will look at the remaining proofs. These are 4 in number, and they are called the proofs of the concurrencies. Following this, we will look at the problems which are associated with the theorems on past leaving certificate papers, and how these should be solved. In Concurrency 1, we are asked to prove that the bisectors of the angles of a triangle are concurrent. This means that the 3 bisectors should intersect at one point, and this is the point O. So we will start out by being given the triangle ABC and the red line BO as the bisector of the angle ABC. We are also given the blue line CO as the bisector of the angle ACB. And these 2 lines intersect at the point O. We are required to prove that the bisector of the third angle BAC will also pass through the point O. Now, before continuing with the proof of this proposition, I want to remind you of what we mean by the distance from a point to a line. Point P to the line L. It is understood that we mean the shortest distance, and this of course is the perpendicular distance from P towards L, as indicated. Every point on the bisector BO is equidistant from the arms AB and BC. Therefore, the point O is as far away from AB as it is from BC. This gives us OX being equal to the length of OY. By a similar reasoning, every point on the line CO, which is the bisector of the angle ACB, is equidistant from the arms BC and AC. Therefore, the length OT is equal to the length OY. Thus we see that OX, OY and OT are all of the same length. In other words, OX is equal to OT. But this means that since every point on the bisector of the angle BAC will be equidistant from the arms BA and AC, and since we have just found out that O is as far away from AB as it is from AC, then O must be on the bisector of the third angle. And that then clenches our proof. Every point on BO is equidistant from AB and BC. Therefore, OX is equal to OY from one of our intercept theorems. Also, every point on CO is equidistant from BC and AC. Therefore, OY is equal to OT. From these 2 lines, we can see that OY is mentioned in both of them. It is equal to OX and it is equal to OT. Therefore, OX must be equal to OT, since both of them were equal to OY. Therefore, O is indeed on the bisector of the third angle BAC because its distance from both arms is equal. Therefore, the 3 bisectors are concurrent. Since OX, OT and OY are all equal, then they are in fact the radii of a circle whose centre is at O and which will be inscribed inside the triangle and having the 3 sides of the triangle as tangents to the circle. The circle is called the incircle, and the point O is called the end-center. In Concurrency 1, we made use of the fact that every point on the bisector of an angle was equidistant from both arms of the angle. And we also made use of the converse of this fact, which is namely that if a point such as W says, I am equidistant from this arm and from this arm, then that point W must be on the bisector T. This is what is known as the converse of a proof. Now in Concurrency 2, we will be making use of a similar converse. In this situation, we are given L as the perpendicular bisector of the line segment AB, and we learned at the intercert that every point on L is equidistant from A and from B, such as this point and all the others as well. So in this case, if a point X points out to the viewer that it is equidistant from A and B, in other words that XA is equal to XB, then that point X has got to be on L. In Concurrency 2, we are required to prove that the perpendicular bisectors of the three sides of a triangle are concurrent. We are given the triangle ABC with K, L and M, the perpendicular bisectors of AC, AB and BC respectively. Note that we are putting the brackets around these to indicate that the line segments are being used. Now L and M intersect at O. And our problem is to prove that the third bisector K will also pass through the point O. So for the time being, we will leave this line somewhat short, and we will leave a question mark over whether or not K passes through the point O. L is the perpendicular bisector of the line segment AB. Therefore, every point of L is as far away from A as it is from B. This privilege is also accorded to the point O. M is the perpendicular bisector of the line segment BC. Therefore, all points along M are as far away from B as they are from C. This privilege is also accorded to the point O. Therefore, O is special because its distance from A is the same as its distance from B and is the same as its distance from C. This means that OA is equal to OC, and therefore, by what I mentioned at the outset, O has got to be on the third bisector K. So therefore, K does indeed travel through O. We can now write our proof as follows. It's very short. Please note that with O as centre and OA as radius, a circle can be drawn which will pass through the points A, B and C. This circle circumscribes the triangle ABC, and it is called the circumcircle, and the point O is called the circumcenter. In the third of our four concurrencies, we will be asked to prove that the perpendiculars from the vertices to the opposite sides of a triangle are concurrent. At the outset, it might be best for you to copy this diagram as we did in some of the proofs of Geometry 1. We are given a triangle ABC. There is a line L from B at right angles to AC. There is another line M from C at right angles to AB. L and M intersect at H. We are required to prove that the third such perpendicular from A this time, namely the line N, it is perpendicular to BC, and we are being asked to prove that it also passes through H. So we write our given and required to prove as follows. The only unusual point here is the use of set notation. L intersection M is the set called a singleton with a single element H. Returning to the diagram, we see that it has become somewhat more complicated. The triangle ABC has been enveloped by a larger triangle XYZ. This has been achieved by a construction, one which you can follow at home by drawing three lines as follows. Through A, draw X and Z parallel to BC. Through B, draw XY parallel to AC. And finally, through C, draw YZ parallel to AB. We write this construction the first thing we look at in our proof is the parallelogram ABCZ. This is a parallelogram because of the construction. AB is parallel to CZ and BC is parallel to AZ. Being a parallelogram, the opposite sides are equal in length. Therefore, the length AB is equal to the length CZ from an intercept theorem. There are other parallelograms in the diagram as well. One of them is A, B, Y, C. This means that AB is also the same length as YC. Consequently, YC, AB and CZ are all equal in length. Therefore, C is in the middle between Y and Z. In other words, C is the midpoint of YZ. Now let us consider the line M. M was at right angles to AB. Therefore, M is also at right angles to YZ. Therefore, we could call M the perpendicular bisector of YZ. By a similar process of reasoning, L is the perpendicular bisector of XY. And N is the perpendicular bisector of XZ. But we have learned in Concurrency 2 that the perpendicular bisectors of the sides of a triangle, in this case the triangle XYZ, are concurrent. Therefore, L, M and N are concurrent and they meet at the point H. So reverting to our original triangle ABC, we have proven that the lines L, M and N do indeed meet at H. H is called the orthocentre, O-R-T-H-O-C-E-N-T-R-E, of the triangle ABC. Can you remember what it would be called for the triangle X, Y, Z? Anyway, in an examination you are free to write the proof any way you wish once the logic is present. However, we normally try to use the mathematical abbreviations. So we have ABCZ is a parallelogram. Why? Because from our construction. Therefore the length AB is equal to the length CZ from an intercept theorem. Also, ABYC is a parallelogram. Therefore AB is equal to the length of YC. Therefore CZ and YC are equal. Therefore C is the midpoint of the line segment from Y to Z. Furthermore, since M was perpendicular to AB, this implies that M is perpendicular to YZ, i.e. M is the perpendicular bisector of YZ. And similarly, L and N are the perpendicular bisectors of the line segments XY and XZ. Therefore L, M and N are concurrent from concurrency 2. That completes the proof of this, the third of our four concurrencies. In concurrency 4, we are asked to prove that the medians of a triangle are concurrent. Now look at the triangle ABC. A median is a line drawn from a vertex to the center of the opposite side. So BY is a median, and so is CX. These two medians intersect at G. We are required to prove that the third median, which will be radiating from A to the middle of BC, we are required to prove that this median also passes through G. This time we will tackle the proof as follows. We will have a construction where we will join A to G. We will continue this line as far again from G to D. We will join B to D and C to D. The line AD intersects BC at Z. We are not saying that Z is the center of BC, because this is what we have to do in the proof. So there is a question mark hanging over this line AD as to whether or not it is a median. When we have completed the proof, we will hopefully have shown that it is indeed a median. In the proof, the first thing we look at is the triangle ABD. In this triangle we have the ratio AX is to XB being the same as AG is to GD. Both ratios are in fact 1 is to 1. From the converse of a previous theorem, this means that the line segment from X to G is parallel to the baseline BD. Of course, XG continues to include GC, so we can say that GC is parallel to BD. Similarly, by examining the triangle ACD and observing that AY is to YC is equal to AG is to GD, we conclude that GY, or if you wish, BG, is parallel to CD. This leads us to the conclusion that BDCG is a parallelogram. Now the diagonals of a parallelogram bisect each other. Therefore Z is the midpoint of BC. This means that AZ was in fact a median. So at this stage we have concluded the proof, but there is one further point which I wish to elaborate upon. And it is this: GZ is half of GD. This means that GZ is half of AG. Or to put it another way, AG is twice the length of GZ. This is what happens when the medians intersect each other. Likewise, CG is twice GX and BG is twice GY. The point G is called the centroid of the triangle ABC. We will now present the proof in examination style format. Firstly, consider the triangle ABD. The ratio AX is to XB is equal to the ratio AG is to GD. This implies that XG is parallel to BD from the converse of one of our previous theorems. Similarly, from the triangle ADC, we get that GY is parallel to DC. Therefore, BDCG is a parallelogram. And consequently, since the diagonals bisect each other, this means that Z is the midpoint of BC. Therefore, AZ was indeed a median. Finally, GD is double the length of GZ. Therefore, AG is double the length of GZ also. That means that AG is to GZ is 2:1. So far in these two tapes, we have gone through the proofs of the theorems and the concurrencies. Each year in the Leaving Certificate, Paper 1, there are 2 complete questions on geometry, and there are 3 parts of question 1, 3 parts out of 10, also on geometry. Now usually the first part of a long question requires you to give the proof of a theorem, and this is then followed by part B, where you are asked questions which are normally related to the theorem that you have proven. Now for the remainder of this tape, we will look at some of the problems which have been associated with the theorems in the past few years of the Leaving Certificate. Now it is only with practice and constant repetition of work that you will become familiar with the solutions of these problems. But there is one point I wish to emphasize to you, and that is that any information which is given to you in the question must be used in the solution of the problem. Nothing is given just to be ignored. And also, keep in mind that the part B of the question is normally associated with the theorem which you have proven in part A. So firstly, let us look at the 1985, Paper 1, Question 4, Part B. Now in Part A, you were asked to prove the theorem regarding the chords of a circle intersecting internally. Whereas the question in Part B shows 2 chords, PS and QR, which intersect at K, which is outside the circle. So from our knowledge of the theorems, we realize that KS times KP is equal to KR times KQ. So we write this down and then proceed to fill in the bits of information which we are given. We have been told that KS is 2 units in length and that KP is 6 units in length. We have furthermore been told that KR is 3 units, and we have been asked to find the length of KQ. So we leave a question mark here. By the way, the diagram is not to scale. So now the problem is simply one of algebra. The 2 sixths, which is 12, is equal to 3 times what? Well, 3 times 4. So therefore our answer is that KQ is equal to 4. This in fact is one of the simpler problems, but of course it is only half of part B. We will return to the other half of part B later. Meanwhile, I want you to consider the 1980 paper. And there was a similar looking diagram involving cords cutting externally. We were told in the question, this was one of the short questions, or the short parts of question 1, that CB, which was the radius, was equal in length to BT, and of course that was equal in length to CA as well. We were furthermore told that the length from T to Q was 9, and that the length from P to Q was 3. Now, as I mentioned in video 1, the length of the cord is not involved in the ratios. So again we write TB times TA equals TQ times TP. And as in the 1985 paper, we start filling in the blanks. Well, TB is unknown, so we will call it X. TA is 3 times the length of TB, so we will call TA 3x. We were given that TQ was 9, and now we do a little bit of calculations and we evaluate that TP is 9 plus 3, which is 12. And then we get 12 times 9, which is 108, equals 3 times x squared. Therefore x squared is 36 and x is 6. Returning to 1985, paper 1, question 4b2. We are asked to prove that the triangles KPR in yellow and KSQ in blue are equiangular. This is done by the candidate writing that the angle SPR is equal in measurement to SQR by virtue of the fact that both angles are standing on the arc SR. The angle SKR, called theta, is a member of both yellow and blue triangles. Consequently, the third angle of each triangle must be equal. This is the obtuse KRP and the obtuse KSQ. We have now proven that the triangles are equiangular, and then we are asked to make use of the result of another theorem which stated that the ratios of the corresponding or matching sides of equiangular triangles are equal. These ratios are PR from the yellow opposite theta is to SQ from the blue, which is opposite theta. We have KP from the yellow opposite the obtuse angle is to KQ from the blue opposite the obtuse angle, and the third ratio is KR from the yellow is to KS from the blue. So having written down these three ratios, we proceed to answer the last part of the question, which is, what is the ratio PR is to SQ equal to? Well, it is equal to the other two. Is 6 is to 4 for KP is to KQ, or 3 is to 2 for KR is to KS. The 6 is to 4 and 3 is to 2 came from part 1 of question 4b. Question 4 of 1983 involves us again with equiangular triangles. Having been asked to prove the theorem, we are presented with a diagram containing many lines inside a circle. One of these lines, AP, is a diameter. Upon hearing this, you should realize that the angle ABP is 90 degrees because it is the angle inside a semicircle. We are also told that the angle AQC is 90 degrees, and we are asked to prove that the blue triangle ABP is equiangular with the green triangle AQC. So we have just shown that each of them contains a 90-degree angle. Next we see that BPA and BCA are both standing on the arc AB, and therefore, from another theorem, these two angles are equal. Consequently, since the third angle of each triangle must be now equal, we have shown that the triangles are equiangular. Finally, we are asked to make use of this fact in finding the length of AQ. So we now extract the ratios of the corresponding sides from the blue and green triangles. We take AB from the blue, which is opposite the angle BPA, and we take the matching side, which is opposite the angle ACQ, namely the side AQ from the green triangle. So we have AB is to AQ being equal to, this time, AP from the blue triangle, which is opposite the 90-degree angle, and AC from the green triangle, which is also opposite the 90-degree angle. So we can then write AB is to AQ equals AP is to AC, and there is no need to involve the third ratio this time. All that remains to do now is to fill in the information which we've been given in the question, which is that AB is 4, AP is 6, and AC is 5. We are left then with one unknown, which is AQ. By cross multiplication, 6 times AQ equals 4 times 5. So we write 6 times AQ equals 20, which means that AQ is equal to 20 over 6, or 3 1/3. This is an unusual type of answer because normally leaving certificate answers are nice round numbers. In 1984, question 3, part 1, we have been asked to prove that the areas of two triangles of equal height are proportional to the lengths of their bases. And in part 2, we are presented with this diagram, and we are asked to extract from it various ratios. And the first one is to look at the triangle ADC and the triangle DKC. So we will firstly concentrate on this section of the diagram. DKC and DAC have the same baseline AKC and have the same height, which would be the perpendicular distance from D to the baseline. Furthermore, since the diagonals of a parallelogram bisect each other, KC is half of AC. Therefore, the base of the little triangle DKC is half the length of the base of the large triangle DAC. Therefore, the ratio of the area of DKC to the area of DAC is 1:2. Next, we are asked to find the ratio between the area of ACD and ATD. At this stage, it would be helpful if you could write down what I call out. ACD is the same area as ABD, because both triangles are standing on the same base AD and lie between the same two parallel lines AD and BC. So again, the area ACD is equal to the area ABD. We are given that T is the midpoint of AB. This means that the area of the triangle ATD is the same as that of the area of the triangle TBD. We will call these areas A. Since the area of the triangle ABD has been shown to be the same as that of the triangle ACD, we conclude that the area of ACD is 2A, and consequently that it is twice the area of AKD. So we can write triangle ACD is twice the triangle ATD, and it is important that these ratios be expressed the right way around. Next, we are asked to consider the area of the triangle KBC. This is half of the area of DBC. Now DBC is another 2A because a diagonal bisects the area of a parallelogram, and we have 2A at the left, so we must have 2A at the right. And this piece here is half of that, which is A again. So consequently, if the area of the triangle ATD is 6 square units, then the area of the triangle KBC must also be 6 square units. Lastly, we are asked to evaluate the ratio AP is to PK. And for this part of the question, all we need is a slimmed down version of the diagram, so we require only A, B, D. AK is a median. DT is a median. Therefore, P is the centroid, and from what we learned in Concurrency 4, the ratio AP is to PK is 2:1. In 1982, question 4, part 3, we meet this diagram. We are given that PK is to KQ is equal to 5:4. We are told that XY is parallel to PQ. This means that these angles RXT and RPK are equal. Also, RTX and RKP because they are corresponding angles. This means that the triangle RTX is equiangular with the triangle RKP. So we can make use of the ratios of corresponding sides of these triangles being equal. We can say that RT from the little triangle is to RK, which is the matching side from the large triangle, is equal to XT from the little triangle and the matching side PK from the large triangle. So we can write RT is to RK equals XT is to PK. Now the reason we do this is because this statement here mentions PK, which we have been told about, and it also mentions XT, which we are being asked to investigate. Now you may ask, why are RT and RK appearing on the scene? Well, shortly they will disappear, but their reason for appearing is to link us in with the other bits of information which we are given and which we are asked to investigate, namely KQ and TY. Because now we switch our attentions to the triangles RTY and RKQ. For similar reasons to the ones on the left, these are also equiangular. Therefore we can say RT from the little triangle on the right is to RK from the large triangle on the right is equal to TY from the little one is to KQ from the large one. So we can write our second line. RT is to RK is equal to TY, which we are investigating, is to KQ, which we were told is 4. Now since the left hand side of both equations is equal, we can say that the right hand sides are equal. So we can write XT is to PK equals TY is to KQ. Now by switching the elements in the diagonal, this would read XT is to TY equals PK is to KQ. Now we were given that PK is to KQ was 5 is to 4, and we had been asked to show in the question that XT is to TY is also 5 is to 4. We have now done this. In 1982 question 3, part B, we are firstly asked to find 3 pairs of triangles which are equal in area. Using QR as base, and since PS is parallel to QR, we have QPR and QSR as one pair. Now using PS as base, we have PSR, PSQ as the second pair of triangles with the same area. Now the third pair is PKQ and SKR. Because PQR and SQR had already been shown to be equal, and by deducting the area of KQR from each, we are left with PKQ on one hand and SKR on the other. Next we are asked to find a ratio of line segments which is equal to the ratio PK is to KR. Now if we consider the triangles PSK, SKR, they have the same baseline, they have the same height, therefore the ratio of their areas is equal to the ratio of their bases. PK is to KR. But the ratio of the area PKS to the area SKR is the same as the ratio of the area PKS to PKQ. So we can now look at these two triangles, PKS, PKQ, and the ratio of their areas is equal to the ratio of their bases, which is SK, KQ. So we can write PK is to KR is equal to SK is to KQ. Next we are asked to find the ratio equal to the area of the triangle PQK and the triangle PKS. This is quite simple. It is just KQ to KS. Because the ratio of the areas is equal to the ratio of the bases, because once again you have the same baseline and the triangles have the same height. Lastly, we are asked to show that the triangle PSK, this little one here, is isosceles. And here we make use of the fact that angles standing on the same arc are equal in measurement. Now look at the arc PQ, and the angle on the circumference PRQ is equal to the angle PSQ. Now since the two lines QR and PS are parallel, and since PR is a transversal, this means that Q or K is alternate with KPS. So therefore these triangles marked in red are all equal. And since the two at the top, left and right, are equal, that means that the triangle PKS must be isosceles. Because in an isosceles triangle, you always have two angles equal in measurement. In 1983, question 3 part 2 asked us to prove the theorem of Pythagoras, which of course is that the square of the hypotenuse is equal to the sum of the squares of the other two sides in a right angled triangle. We are then asked to solve some problems. The first one is that we are given a circle K with a diameter PQ and the line PR equal in length to the diameter, and we are asked to show that S is the midpoint of RQ. Well, since these two sides PR and PQ are equal in length, it means that the angles PRQ and PQR are equal. Furthermore, PSQ is the angle in a semicircle and is therefore 90 degrees. Consequently, PRS and PQS are two equiangular triangles, which means that the angles at the top are equal. Now if we do an axial symmetry in the line PS, the arm PR will fold over onto the arm PQ, and the section from R to S will fold over onto the section from S to Q. And since axial symmetry is preserved length, this means that RS will be the same length as SQ. In other words, S is in the middle. We are then asked to consider the following inequality. Is PQ squared greater than PT squared plus TQ squared? Where T is a point between P and S. So let us mark T in this position. So we are asked, is PQ squared greater than PT squared plus TQ squared? Well, since initially we were asked to prove the theorem of Pythagoras, I suppose now it's appropriate to put it to use. PQ squared is equal to PS squared plus SQ squared, and can be replaced by these two. In the little right angle triangle TSQ, TQ squared is equal to TS squared plus SQ squared. So TS squared plus SQ squared can replace TQ squared. Now we reach the second inequality, and SQ squared appears at both sides, and therefore can be eliminated. So our question now is PS squared greater than PT squared plus TS squared? Well, look at PS. PS is equal to PT plus TS. Squaring both sides of this equation, we get PS squared on the left hand side, and we get PT plus TS multiplied by PT plus TS on the right hand side. Now this is like working out x plus y times x plus y, and the answer in that case would be x squared plus 2xy plus y squared, and this time it is PT squared plus twice PT times TS plus TS squared. That is what we get when we multiply PT plus TS by itself. Well, if PS squared is equal to PT squared plus TS squared plus this extra piece, twice PT by TS, it would be reasonable to assume that PS squared is greater than PT squared plus TS squared on their own. Therefore, this inequality is correct, and there is no need for the question mark anymore. Now, since this inequality is correct, it means that the preceding inequalities were also correct, because each one evolved from the other by the ordinary rules of algebra. So the answer to our question, is PS squared greater than PT squared plus TS squared? Yes. In 1981, question 1 part 6, we are given an isosceles triangle with two sides 5 units in length. We are told that G is the centroid, and we are told that the baseline is 6. Now, since it is an isosceles triangle, this means that the line AG intersects the baseline at 90 degrees. So we have a right angle triangle at the left. Now we are asked to find the length of AG. So we use Pythagoras and we said 3 squared plus x squared equals 5 squared. Now this means that the missing number is 4, because 3 squared plus 4 squared equals 5 squared. So therefore AG on through to the end is 4, and therefore AG itself is 2/3 of 4 because of our ratio 2:1. So the length of AG is 2/3 of 4, or simply 2 2/3. Now this concludes our 2 tapes on geometry. I hope that you have found them informative and that you have picked up some hints in answering the questions associated with the theorems. Some of them are easy, some not so easy, as you have seen. And it is only with constant practice and work that you will be perfect at these.